Hi everyone, and welcome to our video on the ionic product of water, Kw. In this lesson, we'll be focusing on what the ionic product of water is. We're going to be looking at Kw in more detail, and we're going to finish off by looking at some calculations. Make sure you check the description below. I've added some helpful links, including access to lesson resources via Google Drive and information on how you can join our upcoming live sessions. So if we get started now, this is what the specification states. We will be covering all these spec points in this lesson. So if we start off by looking at the ionic product of water. In all aqueous solutions and pure water, the following equilibrium occurs. So we've got H2O and it's dissociating into H plus and OH minus. And just bear in mind that the forward reaction is endothermic. Now, from year one, you would be able to work out the Kc expression for this equilibrium. And you would know that the Kc expression would be Kc equals H plus OH minus all over concentration of your reactants, which was H2O. That's what the Kc expression would be. Okay, now if we rearrange this Kc expression, what we would get is we would basically bring this H2O up and we would have H2O at the top over here. We still have the Kc, and that would be equal to concentration of H plus and OH minus. Okay, now this H2O that we have over here, this is actually a constant, and it's really important that you note that down. The reason why it's a constant is basically because the concentration of water in this equilibrium is much greater than the concentration of H plus or OH minus. That's why this is known as a constant, because the concentration of H2O is much greater, and therefore any changes to that concentration won't really affect the concentration of H plus and OH minus. Therefore, we refer to it as a constant. Okay, now because H2O is a constant, we can literally combine H2O and Kc together and bring out a new sort of name, and that's Kw. Basically, H2O and Kc is basically Kw. It's just a shorter way of saying concentration of H2O and Kc. So our Kw expression is literally the same. It's just Kw equals concentration of H plus and OH minus. As you can see, Kw is just the shortened version of this thing over here, H2O Kc. So instead of writing all this out, you can just write Kw, and that's the expression that you need to know for the exam. Okay, so that's the ionic product of water. And it's really important that you note the Kw expression, as there are a lot of calculations which come up in the exam on this topic. So we've got our Kw expression, which is the concentration of H plus and then the concentration of OH minus. H2O is not in the expression as its concentration is much bigger than all the ions in solution. Therefore, it's assumed to be constant. Now, I've highlighted constant there because I've seen exam questions come up and they've stated why is H2O not included in the Kw expression, and constant is in bold. So it's really important that you note that point down. Okay, now in neutral solutions, neutral as in pH 7, there is an equal amount of hydrogen ions and hydroxide ions in solution. Okay, so originally what we had was Kw equals H plus and OH minus. But if we're looking at neutral solutions, neutral means pH 7, it's clear that there's going to be an equal number of hydrogen ions and hydroxide ions. And because there's an equal number of hydrogen and hydroxide ions, both of these concentrations are going to be the same. So we can simplify the Kw expression even further to Kw equals H plus squared, because we know that the hydroxide ion concentration is just going to be the same as the H plus concentration. So we can just simplify that down to just the hydrogen ion concentration squared. Okay, and then if we square root our answer, we will get the exact hydrogen ion concentration, which would be the same as the hydroxide ion concentration. This will make more sense when we look at some examples later on in this video. Now, remember when I said over here, the forward reaction is endothermic. And it's really important that you know that, because if you increase the temperature, the equilibrium will shift to the right. Why does it shift to the right? Because the forward reaction is endothermic, so it's going to oppose that increase in temperature, and therefore it's going to increase the concentration of hydrogen ions and hydroxide ions. Therefore, Kw will also increase. Okay, and the pH decreases because you've got an increase in hydrogen ions. Okay, so because we're increasing the number of hydrogen ions, remember Kw was H plus squared, and we've got a neutral solution, the pH will decrease. Kw will increase because we're favoring the forward reaction. However, the pH itself would decrease because if we're shifting forward, the number of hydrogen ions in solution will increase, therefore causing the pH to decrease. We're referring to this expression. We're assuming that there's an equal amount of hydrogen ions and hydroxide ions in solution. Okay. Now, to finish off, we're going to have a look at some examples, some calculations. Okay, and normally of water, the Kw is 1 times 10 to the power of negative 14, but you will be given that in an exam. Okay, so if we have a look at the first question, it says calculate the pH of the following solutions. 0.15 mole per dm cubed of potassium hydroxide. How do we do this? Okay, so we're given Kw, so we know that it's going to be referring to Kw equals H plus OH minus. Okay, now we know that the value of Kw is 1 times 10 to the power of negative 14. So we're going to have 1 times 10 to the power of negative 14 equals H plus. So remember, this is a potassium hydroxide. So the OH, because there's an OH over here, this is the concentration of hydroxide ions in solution. So we don't know the concentration of hydrogen ions, so we're going to leave that like that. But we do know the concentration of hydroxide ions. That is 0.15. The reason why we know it, it's because this is potassium hydroxide. There's a OH in the compound, therefore any concentration will be referring to the concentration of hydroxide ions. So it was 0.15. Okay, now we can just rearrange to work out the hydrogen ion concentration. So we've got the hydrogen ion concentration will be equal to 1 times 10 to the power of negative 14 divided by 0.15. Okay, and then you can just type this into your calculator. So we've got 1 times 10 to the power of negative 14 divided by 0.15. That will get you 6.6 reoccurring times 10 to the power of negative 14. Okay, and this is the hydrogen ion concentration. Now, it says calculate the pH. We know that when we know the hydrogen ion concentration, we can just negative log base 10 our answer, and that would get us our pH. So if we negative log base 10 our answer, we would get an answer of 13.18 to 2 decimal places. Okay, and that's our answer there. Next question says 0.05 mole per dm cubed of sodium hydroxide. Again, it's referring to hydroxide ions. So we know that it's going to be referring to the hydroxide ion concentration in the Kw expression. So we know that our Kw is 1 times 10 to the power of negative 14. We don't know our hydrogen ion concentration. And our hydroxide ion concentration is 0.05. Okay, same thing over here. We're going to rearrange. So we're going to get H plus equals divided by 0.05. And then whatever answer we get over here, we're going to negative log base 10 our answer. Okay, so if I just do that, so we've got negative log base 10 of 1 times 10 to the power of negative 14 divided by 0.05. And that would get us an answer of 12.70 to 2 decimal places. Okay. Now it says 0.2 mole per dm cubed of barium hydroxide. Okay, again, it's referring to hydroxides. So we know that we're going to be using this concentration of hydroxide ions. Now, there's a difference over here. This has a number 2 over here. Okay, that means we will need to multiply the hydroxide ion concentration by 2. So Kw is 1 times 10 to the power of negative 14. We still don't know our hydrogen ion concentration. Our hydroxide ion concentration, we know it's going to be 0.2 multiplied by 2. And the reason why it's that is because there's a small 2 over here next to the hydroxide ions, which means there are 2 lots of hydroxide ions for every 1 barium ion. Okay, so that means whatever concentration we have over here, we would need to multiply it by 2. Okay, so same concept over here. We're going to have the hydrogen ion concentration to be 1 times 10 to the power of negative 14 divided by 0.4. And then whatever answer we get over here, we're going to negative log base 10. And we're going to give our answer to 2 decimal places. So we're going to negative log base 10 of 1 times 10 to the power of negative 14 divided by 0.4, and that gives us an answer of 13.60 to 2 decimal places. Okay, now if we move on to 2 more examples, it says calculate the concentration of the following bases. Okay, this time we're given the pH. So how are we going to do this? Whenever we're given the pH, always work out the hydrogen ion concentration, and then you can work from that. How do we do that? Remember, it's 10 to the power of negative pH. So it's going to be 10 to the power of negative 14.3. That's going to give us an answer of 5.01187 multiplied by 10 to the power of negative 15. That's our hydrogen ion concentration. And what we're going to do over here, we're going to use our Kw expression. One times 10 to the power of negative 14 equals our hydrogen ion concentration, which is, I'm just going to write answer over here, and then our hydroxide ion concentration. Okay, and to work out the hydroxide ion concentration, we're just going to do 1 times 10 to the power of negative 14 divided by our answer. And that's going to give us an answer of 1.99526. But remember, our answer needs to be quoted to 2 decimal places. So it's going to be equal to 2.00. So I'm just going to write it over here. 2.00 and this is the concentration, so it's going to be mole per dm cubed. Okay, now barium hydroxide with a pH of 12.50. So again, we're going to start off by doing 10 to the power of negative 12.50. And that's going to give us an answer of 3.1627766 multiplied by 10 to the power of minus 13. Okay, and this is the hydrogen ion concentration. So we're going to use our Kw expression, which was 1 times 10 to the power of minus 14 equals our answer, which we've just got over here, and then the hydroxide ion concentration. Okay, so we're going to do 1 times 10 to the power of negative 14 divided by our answer, and that's going to give us 0.031622766, and this is our hydroxide ion concentration. However, you would have realized that we have a small 2 over here. Okay, so we would need to remember, in this case over here, we multiplied our answer by 2. Over here, we have to do the opposite, because this is the hydroxide ion concentration, including the 2. But we want it in this format, where it's giving you the hydroxide ion concentration for 1 hydroxide ion. So what we have to do over here, we would need to divide by 2. Okay, and if we divide that by 2, we would get an answer of 0.016. I've just written it there to 2 significant figures. Okay, and that's your final answer there. Okay, now there's a lot of working out. I'm just going to highlight the answers. So we've got 2 there, and we've got 0.016 there. Okay, and those were some examples of questions that you could come up with in an exam. And that's it for this video. If you have any questions, feel free to drop them in the comments below. Don't forget to check the description for any useful resources and to sign up to our live sessions. If you'd like to support us, you can buy us a coffee using the link in the description. Thanks so much for watching, and I hope to see you in the next video.